Imagine a clock whose hands tick backward, a clock that doesn't just measure time but mocks it, running in defiance of every rule you thought governed the universe. Imagine a world where cause trails effect, where a footprint forms in the sand before the step falls. Such imagery belongs to myth, to philosophy, to fiction. Yet in the cold silence of a Toronto laboratory, reality itself seemed to play this impossible trick. What if time, the most fundamental thread of our existence, could bend? What if, for the briefest of instants, it could even turn negative? For centuries, time has been treated as the bedrock of our lives, immutable, relentless, unforgiving. Empires have risen and fallen under its gaze. Stars have burned and collapsed by its measure. To our minds, time is the most linear of rivers, flowing inexorably forward. But under the microscope of quantum physics, that river ripples strangely, currents crossing, eddies forming. And sometimes, as the team at the University of Toronto has now shown, it seems to reverse entirely. This isn't science fiction, it is measurement, cold numbers, recorded with merciless precision. A photon, a particle of light, entering a cloud of rubidium atoms, its dance observed by the finest instruments science can wield. And when the data is traced, when every uncertainty is stripped away, one result stands naked on the page: negative time. How can this be? How can something interact with matter for less than zero time? How can atoms respond before they are even touched? The answer begins not with laboratories and lasers, but with something familiar: a stadium filled with thousands of people. Picture a crowd rising and sitting, arms waving in sequence. No single person moves faster than the human body allows, and yet the wave sweeps around the arena with impossible speed. The motion is not in the individuals, but in the pattern. Light behaves the same. A pulse of light is not a simple note, but a chord, a blend of many frequencies layered together. When it passes through atoms, each frequency shifts slightly, and when they recombine, the whole wave can change its shape, its crest appearing sooner than expected, like the wave in the stadium racing ahead of the fans themselves. For decades, physicists dismissed this effect. They called it pulse reshaping, a sleight of hand. Nothing truly arrived early, they insisted. Nothing physical broke the rules. But there was always a question lingering at the edge of the argument. If nothing broke the rules, why did the mathematics predict negative times? Why did the equations insist that under certain conditions, the peak of a pulse could leave before it should? Enter Ephraim Steinberg and Daniela Angulo, the architects of a new experiment. Their goal was deceptively simple: to decide whether negative time was a trick of the eye or a measurable feature of reality. To answer the question, they would have to watch light at its faintest, at the level of individual photons, as it brushed past atoms chilled to a whisper above absolute zero. This was no ordinary experiment. It required cooling rubidium-85 atoms until they formed a tiny, ghostly cloud suspended by magnetic fields in near-perfect isolation. Through this cloud, the team fired the gentlest possible pulses of light, so faint that only single photons could be tracked. To measure what happened inside, they paired the signal with a second beam, a probe tuned like a stethoscope to the atom's heartbeat. Then they waited. What they found should have been impossible. The probe revealed that when a photon passed through, the atoms responded with tiny changes in their state. But the timing of those changes did not always line up with expectation. In some cases, the atoms appeared to return to rest before they had ever been excited. The recorded interval of excitation was negative. Let that sink in. A particle entered, and the response of matter marked its passage not after, but before, as if the atoms anticipated the touch of light. This was the moment when the debate ended. For years, skeptics claimed negative group delay was just an illusion, that the pulse had been reshaped, but no physical system had actually experienced a negative time. Steinberg's team proved otherwise. The atoms themselves, the heart of the interaction, bore the signature of negative time. But this is not the end of the story. It is only the opening crack in the door. Because if time can appear negative in the quantum world, what else might bend? What else might fracture? And if our most fundamental measure of reality is malleable, then what does it mean to say anything happens before, or after, or at all? The experiment gives us no paradox machines, no journeys into yesterday. Causality remains intact, inviolate. But beneath the rules, something stranger whispers, a reminder that our experience of time is not absolute, that time is not the master we imagine, but a pattern, an interference, a construct. And so we begin our journey into the strange corridors of negative time, where photons appear to escape before capture, where atoms seem to anticipate the future, and where the very definition of now unravels. Because if even the smallest fragments of the universe can slip free of time's grip, what hope have we of ever understanding the true shape of reality? The strange behavior of light, this whisper of negative time, cannot be understood by looking at photons as little bullets racing through the void. That image belongs to the comforting simplicity of high school textbooks. In reality, light is both particle and wave, both local and extended, both a discrete spark and a spreading ripple across space. To grasp how a photon could seem to arrive too early, we must first imagine the wave. Picture yourself in a stadium, seated among tens of thousands. The game is tense, but in the stands, the crowd has decided to make its own spectacle. Someone rises, arms outstretched, then another, then another. A wave of motion builds, racing along the bleachers. But look closer. No single fan moves faster than a human can stand and sit. The wave itself, however, sweeps across the stadium at a speed greater than any individual action. It is not a person who moves fast. It is the pattern. This is the key to understanding light. A light pulse is not a single pure frequency, but a symphony, a chord struck across the strings of the universe. Each frequency is like a fan in the stadium, shifting in its own time, its own rhythm. When the pulse enters matter, say a cloud of atoms chilled to the edge of absolute zero, each frequency slows and shifts differently. Some are delayed, some bent aside, some reshaped. But when the chord recombines, the crest of the wavefront may appear ahead of where it ought to be. Like the stadium wave leaping around the arena, the light pulse seems to arrive early. This is not faster than light travel. No law of relativity has been broken. Instead, it is interference, a reshaping of the pattern. Yet the effect is striking. The peak emerges before it should, as though reality itself had been cheated. For decades, scientists who observed this effect shrugged it off as sleight of hand. Group velocity, they called it, the apparent speed of the pulse as a whole, distinct from the motion of any individual photon. An illusion, a mathematical trick. Nothing truly traveled faster than light, they insisted, and certainly nothing traversed time in reverse. And yet doubt remained. Because if it were truly just an illusion, the mathematics would not be so insistent. The equations predicted that under precise conditions, short enough pulses, atoms tuned to just the right resonances, the group delay could dip below zero, not just small, not just peculiar, but negative. The pulse peak would not only race ahead, it would appear to leap forward into time it had not yet entered. The analogy of the stadium wave is comforting, but incomplete, because here the crowd is not people but frequencies, and they do not simply sit or stand, they shift in phase, bending in ways that overlap and cancel, producing shapes never seen before. A single crest may rise from nothing and vanish as quickly. To the detectors, it is as though the pulse has emerged before the input has even been fully delivered. Still, skeptics held their ground. They argued it was only reshaping, a trick of perspective. Like a magician producing a coin from thin air, there was no miracle, only misdirection. But the University of Toronto team refused to be satisfied with this dismissal. If the crest appeared early, then surely matter itself would record that early arrival. If light interacted with atoms at negative time, the atoms should carry the signature of that interaction. And so they built the experiment, one designed not to watch the wave, but to listen to the atoms themselves. Imagine a cloud of rubidium-85 suspended by magnetic fields, cooled to a temperature where atomic motion slows to nearly nothing. In this near-perfect stillness, two beams of light are cast. One, the signal, the pulse under scrutiny. The other, a probe, tuned slightly away from resonance, its task to monitor the atom's heartbeat. The signal strikes, photons brushing the atoms, and the probe records how long the atoms remain excited. It is here, in this theater of chilled atoms and whispering light, that the impossible occurs. Because when the data is examined, when the excitation times are charted, the atoms tell a story no one expected. Sometimes they respond negatively. They return to rest before the interaction has even begun. How can this be? How can atoms anticipate a photon, respond before the event, as though they had glimpsed the future? The skeptics insist again, it is only reshaping. Nothing has truly violated causality. But Steinberg and Angulo are unmoved. The atoms are not an illusion, they are matter, recording the event. And their record is clear, the interaction time is negative. This is where physics becomes philosophy. Because if the atoms themselves record negative time, then what is time in the first place? Is it a line? Is it an arrow? Or is it, like the wave in the stadium, a pattern that can twist and fold, creating shapes that mock our intuitions of before and after? The crowd rises and sits, and the wave moves. But what if the wave crests before anyone has even stood? What if the pattern itself is not bound by the sequence of its parts? We are forced to ask, what does it mean to measure time in a world where time itself is not absolute? What does it mean for cause and effect when the effect seems to slip free of the cause? For now, the answers remain elusive, but the experiment is only beginning, and in the shadows of that laboratory, deeper questions await. Because the wave is only the first glimpse. Beyond it lies a stranger truth, that even atoms, the heart of matter itself, can tell time differently. And when atoms disagree with our clocks, when their heartbeat contradicts the arrow of time itself, how can we be certain we know what time really is? For centuries, the laws of physics have been written in a language of certainty. From Galileo dropping spheres in Pisa to Newton's apple tumbling through the air, we believed the universe could be understood through careful observation and simple rules. Light slowed when it passed through glass. Atoms absorbed and re-emitted energy in predictable ways. Time, that relentless current, always pressed forward. In this framework, cause and effect ruled. Strike a match and flame follows. Push a stone and the stone rolls. The future was sculpted by the past, and the arrow of time stretched endlessly forward. When light met matter, the story was thought to be equally straightforward. A photon strikes an atom, is absorbed, and the atom shifts to an excited state. For a fraction of a second, it holds this energy like a spring wound tight. Then, as it relaxes, the photon is re-emitted. Energy in, energy out. No tricks, no mysteries. In the macroscopic world, we see this play out every day. Sunlight passes through a glass of water, slowing slightly, bending as it enters, bending again as it leaves. Rainbows form as wavelengths separate, each frequency refracting at its own angle. It is all elegant, all predictable. Physics called this refractive index, a number that told us exactly how much slower light would move through a medium than through empty space. To the human eye, it was the reason a stick looks bent when dipped into water, why diamonds sparkle, why sunsets blaze red. The rules were clear, the math precise. When the 19th century brought the wave theory of light, it deepened but did not break this clarity. Light was not simply a stream of particles, but a wave oscillating through the ether. When it encountered matter, the wave slowed as it passed from one medium to another, not because the photons themselves were sluggish, but because they danced with atoms, being absorbed and re-emitted, slowed by the constant exchange. This model explains so much: the way glass lenses could bend light to focus images, the shimmering colors of oil on water, the way sound waves and water waves shared common principles. A photon entered matter, the atom caught it, held it for a fraction of a second, then let it go. A chain of tiny handoffs that slowed the overall progress of the wave. Time in this story was always positive. The atom always responded after the photon arrived, never before. Quantum mechanics, when it emerged in the 20th century, complicated the story, but did not shatter it. Yes, photons were quanta, discrete packets of energy. Yes, atoms absorbed them in jumps between quantized states, but the sequence of events remained intact. Photon first, atom second, before and after. Input, then response. Even relativity, Einstein's great dismantling of Newton's absolutes, preserved this order. Nothing outran light. Nothing reversed causality. Space and time were flexible, yes, stretched by motion, bent by gravity, but the arrow remained unbroken. The future came after the past. We built technologies on this bedrock. Cameras, fiber optics, lasers, satellites, all engineered on the principle that light travels predictably through matter. Our global internet pulses with photons streaming through glass fibers, slowed slightly but never reversed, carrying information in a relentless forward march. This was the physics we thought we knew, safe, reliable, a cosmos where time could be trusted. But trust is dangerous. Trust blinds. And beneath this reassuring surface, questions simmered. Why, under certain circumstances, did the peak of a light pulse emerge earlier than expected? Why did equations predict negative group delays, times less than zero? Was it truly just reshaping, a trick of interference, or was something deeper occurring? The skeptics clung to the story of illusions. But the math, with its cold indifference, whispered otherwise. Under the right conditions, pulses short enough, atoms tuned precisely, time itself seemed to falter. The physics we thought we knew could not account for it, at least not in any way that left our intuitions intact. Because if an atom's excitation could appear to end before it began, then the old handoff story, photon first, atom second, no longer held. Imagine a runner passing a baton, only for the finish line to record the baton's arrival before it left the runner's hand. No law was broken, and yet the narrative collapsed. The baton moved as expected, but the story of before and after had twisted. This is what the Toronto team uncovered. Not the destruction of physics, but its distortion. A reminder that the universe does not bend itself to fit our metaphors, our models, our human craving for sequence. Instead, it reveals cracks in the surface and dares us to look deeper. And so, the old rules must be revisited. The story of refraction and handoffs, of absorption and emission, was never the full truth. It was a shadow cast by something stranger, a quantum interference of frequencies, overlapping in ways our minds cannot intuit. But if the old physics is a shadow, what is the substance that casts it? What lies beneath the illusions of slowing light and predictable time? The answer, if there is an answer, lies in the next layer of the experiment. In the attempt not just to observe the wave, but to measure the atoms themselves. To listen to their heartbeat as light passes through and to discover whether their memory of the interaction matches ours. And when their memory speaks, it will tell a story far more unsettling. Because if the atoms themselves bear witness to negative time, then our entire understanding of before and after must be reimagined. This is where the comfort of classical physics ends, where the arrow of time begins to blur, and where the universe reveals that even the rules we trusted most are only approximations of a truth we are not yet prepared to face. Because what is time if even matter itself cannot keep it straight? Every era of science has its taboos, results too strange, too disruptive to be taken seriously. Often they arrive as fleeting anomalies, small cracks in the walls of certainty. And almost always, the instinct of the scientific establishment is to plaster them over, to declare them errors of measurement, tricks of perspective, illusions unworthy of pursuit. Negative time was one of these taboos. The idea had lingered at the edges of physics for decades, a whisper in the mathematics of wave propagation. When scientists studied how light pulses traveled through materials, the equations sometimes yielded curious predictions. Under rare conditions, the pulse peak could exit earlier than expected. In the language of group velocity, this meant a negative delay, as though the signal had arrived before it should. At first, no one quite believed it. A pulse emerging early was unsettling enough. But negative time? That was heresy. Time was not a variable to be toyed with. Time was the ground upon which all physics stood. Experiments were performed, of course. Physicists are nothing if not persistent. In laboratories across the world, pulses of light were fired through transparent materials, through optical fibers, through atomic vapors. And indeed, the results sometimes seemed to confirm the impossible. Peaks shifted forward, outputs emerged in ways that suggested time itself had bent. But the interpretation was always cautious, even dismissive. Pulse reshaping, they said. The crest you saw emerge early was not the same crest that entered. The pulse had distorted, frequencies interfering, the wavefront recombining into a new shape. Nothing had actually traveled faster than light. Nothing had violated causality. Negative time, they insisted, was not real. It was a clever defense, and a comforting one, because it meant that physics was safe. It meant that the strange results could be filed away as curiosities, not revelations. To admit otherwise would have been to question too much: the meaning of before and after, the sequence of cause and effect, the very arrow of time itself. And so the old dismissal became a reflex. Whenever negative group delay appeared, physicists waved it aside. A mirage, a trick of the instruments, a mathematical artifact with no physical meaning. Even in journals, the language revealed the unease. Papers would describe the phenomenon, but always with caveats. Apparent superluminality, anomalous dispersion, reshaping effects. Never negative time. Never the suggestion that the atoms themselves might be experiencing something profound. The fear was not irrational. Physics had been burned before by seductive illusions. The 19th century was full of them: perpetual motion machines, caloric fluids, luminiferous ether. Each seemed plausible, even obvious, until they collapsed under scrutiny. No one wanted to be caught chasing another ghost. And yet the whispers persisted, because the mathematics would not stay quiet. The equations, indifferent to human caution, continued to predict strange results: negative delays, negative excitation times, predictions that seemed to mock the old dismissal. It is easy to see now why the skeptics clung to denial. To accept negative time would have meant revisiting the very foundations of physics. It would have meant questioning the reality of time itself. And what could be more unsettling? Imagine a courtroom where every witness insists on the same story, except for one. A single voice contradicts the consensus, testifying that the event happened before it began. Do you dismiss the witness as mistaken, or do you question the trial itself? Most physicists chose the former, but there were always a few who listened, a few who asked whether the witness, however strange, might be telling the truth. Among them was Ephraim Steinberg, who grew impatient with the evasions. If negative time was truly just an illusion, then the atoms themselves should not bear its mark. But if the atoms did record it, if their excitation and relaxation matched the negative delay, then the old dismissal would collapse. The skepticism was not without merit. Science depends on caution, on restraint. But it also depends on daring, on the willingness to stare into the abyss of paradox and ask, what if? For years, the community had looked away, soothing itself with the story of pulse reshaping. It was elegant, it was safe, and it preserved the comforting story of time. But the Toronto team refused to look away. They wanted to know whether matter itself agreed with the illusion or whether it would testify to something stranger. And so, a new experiment was born. One designed not to watch the pulse, but to listen to the atoms. Not to measure the crest of the wave, but the heartbeat of matter as it danced with light. If the atoms confirmed the old dismissal, then the case would be closed forever. But if they did not, if they recorded negative time, then the taboo would shatter. This was the gamble, the risk of ridicule, because to measure negative time was to suggest that time itself might not be as absolute as we believe. To suggest that before and after are not immutable truths, but patterns, shapes in the interference of waves. It was a gamble worth taking, because if physics teaches us anything, it is that the strangest anomalies often reveal the deepest truths. In the past, scientists dismissed meteors as atmospheric phenomena until stones were collected from the fields. They dismissed continental drift as fantasy until the plates were mapped. They dismissed quantum entanglement as spooky action until experiments proved it real. Perhaps negative time, too, was no illusion. Perhaps it was the next ghost waiting to become real. And if so, then the old dismissal was not caution. It was blindness, a refusal to follow the evidence where it led. The Toronto experiment would not just measure light, it would measure courage, the courage to ask whether time itself can lie. And when the results arrived, they would speak with unsettling clarity. Because the atoms do not care about human fears, they do not cling to the comfort of linearity, they do not hesitate to tell us the truth. And their truth was this: sometimes the arrow of time bends backward. Science is not made of grand pronouncements. It is built in the quiet hum of machines, in the precision of lasers aligned to a fraction of a degree, in the silence of a laboratory where the air itself seems to hold its breath. If you had walked into the University of Toronto's quantum optics lab during those months of preparation, you would not have seen drama. You would have seen patience, a team of researchers calibrating, adjusting, waiting. But behind their calm movements lay a single, audacious question. Can time itself be measured as negative? To answer it, they would need to construct an experiment on the very edge of possibility. For decades, physicists had argued that negative time was an illusion. Steinberg and Angulo sought to prove whether the illusion left fingerprints in matter itself. The key was not simply to observe the pulse of light, but to listen to how atoms responded when it passed through. The atoms of choice were rubidium-85, not because they were exotic, but because their properties could be tuned with extraordinary precision. These atoms, suspended in a magneto-optical trap, would become the witnesses in this trial of time. To prepare them, the team had to cool them to near absolute zero, temperatures so low that their random motion slowed to a crawl, their chaotic dance reduced to the faintest shiver. Only then would their responses be clear enough to record. Imagine the scene. A glass chamber suspended in the heart of the lab, glowing faintly with the cold light of lasers. Inside, a cloud of atoms hovered like ghostly dust, invisible to the naked eye. Around them, instruments lined the tables, detectors sensitive enough to count individual photons, electronics tuned to capture infinitesimal shifts in phase and frequency. Every detail mattered. Every fluctuation of temperature, every vibration in the room could disrupt the fragile balance. The signal was a carefully sculpted pulse of light, faint enough to be reduced to single photons. In ordinary experiments, a flood of photons might mask the subtleties of interaction. Here, subtleties were the entire point. By working at the quantum level, photon by photon, the team could watch each event unfold with clarity. But a signal alone would not be enough. They needed a witness. For that, they introduced a second beam, the probe. Its task was not to disturb, but to observe, slipping through the atoms without being absorbed, tuned slightly away from resonance. Like a stethoscope pressed to a beating heart, it would detect the tiniest changes in the atom's state. This dual beam system was the core of the experiment, one beam to initiate, one beam to record. As the signal pulse entered the atomic cloud, the atoms would absorb and respond. The probe, sensitive to these changes, would reveal exactly how long the atoms remained in their excited state. That interval, excitation to relaxation, would be the measure of time itself. In principle, it was simple. In practice, it was brutal. Aligning the beams demanded surgical precision. Calibrating detectors to register single photons required weeks of iteration, and the atoms, so fragile in their cold state, demanded an environment free from interference. Even the vibration of footsteps in the corridor could ruin a trial. But this was the price of chasing the impossible. To measure negative time, they had to build an experiment where no error could be blamed, no artifact could be dismissed. If the atoms themselves recorded a negative interval, then it would not be illusion, it would be reality. There is a kind of poetry in this setup. Human beings, born of stars and dust, building machines to trap atoms and slow them to a whisper, firing pulses of light so faint they could be counted one by one, and in that stillness, listening for the heartbeat of time. Weeks became months as the apparatus took shape. The rubidium cloud was prepared, the lasers tuned, the detectors tested. Data began to flow, streams of numbers marking the arrival and departure of photons, the corresponding shifts in the probe beam. At first, the results were exactly as expected, positive intervals, atoms excited after photons arrived, the story of cause and effect intact. But science, true science, is not about confirming what you already believe. It is about finding the moments when reality betrays your expectations, and then following those betrayals into the unknown. It was in the longer runs, under specific conditions of pulse duration and density, that the anomalies appeared. The probe revealed atoms returning to their ground state before they had ever seemed to be excited. Negative intervals. A record of events that contradicted the very sequence upon which physics had been built. The team checked, rechecked, recalibrated. Were the detectors misfiring? Was there interference from stray fields? Was the probe itself distorting the measurement? Every possibility was tested, every flaw ruled out, and still the results persisted. Negative time. To see such numbers on a page must have been surreal. Hours of meticulous work distilled into figures that declared the impossible. It is one thing to imagine negative time in equations, to dismiss it as artifact. It is another to watch it emerge from your own apparatus, undeniable, repeatable, real. The magnitude was small, fractions of nanoseconds, slivers of interaction, but the meaning was vast. Because it confirmed that negative time was not just a trick of the pulse. It was etched into the response of matter itself. The atoms had testified, and their testimony was clear, and here perhaps lies the most haunting truth. The experiment was not extravagant. It was not built in the caverns of a particle accelerator or the billion-dollar halls of a space observatory. It was a modest room in Toronto, a handful of researchers, a cloud of atoms suspended in silence. And yet, in that room, the arrow of time cracked. From the outside, you would not have seen the rupture. You would have seen graduate students sipping coffee, scribbling notes, adjusting optics. But beneath that surface, something more profound was unfolding. The universe was revealing one of its darkest secrets. This is the paradox of science. The most ordinary spaces can conceal the most extraordinary truths, and the quietest experiments can echo across the centuries. The Toronto experiment was not the end of the debate, but it was the beginning of the end of denial, because once atoms recorded negative time, the old dismissal could no longer hold. The taboo had been broken, and if atoms can record negative time, then what does that mean for the rest of us? What does it mean for a universe where every heartbeat, every memory, every moment of our lives is measured against the relentless forward march of time? What if that march is not as relentless as we thought? There are moments in science when the numbers on a screen seem to mock you. You stare, waiting for them to shift, to resolve into something ordinary. But they do not. They remain where they are, steady, insistent, whispering that the world is not as you believed. For Steinberg's team, that moment came not with a dramatic flash of light, but with a quiet reading on a detector, a trace drawn across a screen. At first glance, it was nothing unusual. A photon entered the atomic cloud. The probe beam responded. Data points scattered into a neat curve, a typical run in an experiment of countless repetitions. But the curve did not stop where it should have. It fell below zero. The atom's recorded excitation time, the interval between absorbing energy and releasing it, was negative. They had returned to their ground state before they were ever fully excited. In other words, the atoms seemed to have completed their response before the cause had even finished arriving. In the sterile glow of the laboratory, no one shouted. No champagne corks were popped. Instead, there was silence, because the weight of what they were seeing was too heavy for celebration. Negative time. For decades, physicists had argued about whether such results were illusions. Now here it was. The atoms themselves carried the mark of the impossible. The instinct, of course, was suspicion. Could the detectors be misaligned? Could stray fields have corrupted the signal? The researchers retraced every step. They recalibrated the photon counters, checked the laser stability, varied the intensity of the probe. But the results held steady. The anomaly persisted. In some runs, the intervals were positive, as expected. In others, they hovered near zero. But under precise conditions, certain pulse durations, certain densities of atoms, the times turned negative, consistently, repeatably. For the first time, negative group delay was not just a mathematical curiosity, not just the crest of a pulse reshaping itself. It was a physical record written into the atoms themselves. And that changed everything, because illusions do not leave fingerprints. Tricks of perspective do not alter the heartbeat of matter. If the atoms remembered negative time, then something real had happened. Something far stranger than any illusion could explain. Imagine a shadow moving before the body that casts it. Imagine an echo that precedes the shout. These were the metaphors that flooded the mind, and yet none could fully capture the strangeness. The atoms had spoken, and their testimony was clear. The sequence of events was not what we thought. But how could it be? How could matter respond before the photon had even finished passing through? The answer lay not in paradox, but in interference. A light pulse is a symphony of frequencies. Each is shifted slightly as it passes through atoms, delayed or advanced by fractions. When these frequencies recombine, the crest of the pulse can move forward, appearing earlier than expected. The atoms tuned to these frequencies register the shift. Their excitation is pulled forward with it, like dancers following a rhythm that seems to anticipate the beat. Nothing truly travels backward in time. No information escapes into the past. Causality remains intact. And yet, the measurement is real. The atoms have lived through an interval that registers as less than zero. The strangeness is not in what happens, but in how we describe it. Our words, before, after, delay, duration, are blunt tools against the precision of quantum interference. We want to tell stories of cause and effect, of input and output. But the quantum world does not obey our stories. It obeys mathematics, and mathematics alone. Still, the human mind cannot help but recoil. Negative time is more than a technical detail. It is an assault on intuition. Time is the fabric upon which we drape our lives, the measure of every memory, every heartbeat. To see it bend is to feel the ground shift beneath us. The team pressed on. They varied the pulse shapes, the densities of atoms, the tuning of the probe. Each adjustment confirmed the pattern. Negative times appeared exactly where theory predicted. The match was perfect, unsettlingly perfect. When Steinberg spoke of the results, he was careful. He did not claim time itself had reversed. He did not suggest photons had traveled backward. Instead, he described the phenomenon as a fruitful way to describe the results, a cautious phrase, and yet it carried a quiet revolution. Because to describe negative time as real was to admit that the old dismissal no longer held. Outside the lab, the implications rippled outward. Physicists who had long argued that negative group delay was a mere artifact now faced evidence that it left a measurable mark on matter. The debate was not over, but the ground beneath it had shifted. Inside the lab, the mood was less dramatic but no less profound. For the students and researchers who had spent months calibrating lasers and counting photons, the discovery was both exhilarating and humbling. They had glimpsed something at the edge of comprehension, a truth that felt both undeniable and impossible. And yet, the work was only beginning, because to measure negative time was one thing, to understand it was another. If atoms could record negative intervals, what did that mean for our conception of time itself? Was time truly a river, flowing endlessly forward? Or was it more like a wave, patterns forming and dissolving, sometimes seeming to run against the current? The questions multiplied, each more unsettling than the last. And as they multiplied, so too did the sense of wonder. Because in those fractions of a nanosecond, in those negative intervals, the universe had revealed one of its strangest secrets. That time, the master we thought unbreakable, could be bent, twisted, reshaped. And if time can be reshaped in the quiet of a laboratory, who is to say it cannot be reshaped on grander scales? Who is to say the cosmos itself is not threaded with negative intervals, hidden from our perception but woven into its fabric? This is the cliff edge upon which the experiment balanced. The data was clear. The atoms had spoken, but their testimony raised more questions than it answered. What is time if even atoms can contradict it? And if atoms can, what about us? The first instinct when confronted with negative time is panic. If atoms can respond before they are touched, does that not mean the universe has slipped its leash? If photons can emerge from matter earlier than they should, does that not mean causality, the bedrock of reason itself, has been shattered? It is a tempting conclusion, but like so many things in quantum mechanics, the truth is both stranger and subtler. Because the universe has not betrayed its rules, the speed of light has not been violated, the sacred chain of cause and effect has not been severed. What has happened is something else, something that hides in the gaps between our intuitions. Interference. Light is not a single voice, it is a chorus. Each pulse of light, no matter how faint, is not one frequency but many, stacked together like the notes of a chord. When this pulse encounters atoms, each frequency is altered slightly differently. Some are delayed, some are advanced, some are nudged into new alignments, and when those frequencies are woven back together, they do not return to their original shape. They interfere. Some add, some cancel, some shift. Out of this interference, a new pulse emerges, one whose crest may appear sooner than the original would suggest. This is negative group delay, not a photon racing backward through time, not an atom whispering to the past, but a reshaping, a rearrangement of patterns so that the peak of the wave is pushed forward. Think again of the stadium wave. Each fan stands and sits in their own time. No one cheats, no one violates the rules of their body. But the pattern that emerges can sweep around the arena at dizzying speeds, faster than any individual could move. It is not the people who travel, it is the interference of their actions. In the quantum world, the analogy deepens. The frequencies of light are like those fans, each shifting in its own rhythm. When combined, their interference builds a crest that leaps forward, and the atoms, tuned to those frequencies, record the leap. Their excitation and relaxation reflect the interference. And so, their time appears negative. And this is the key. No single photon travels backward in time. No information escapes into the past. Causality survives. What changes is our description. Because when we speak of time, of before and after. We imagine a line, clean, simple, absolute. But what if time is not a line? What if it is a wave? A wave can bend, it can crest early, it can shift and fold. And in those folds, we glimpse results that seem impossible but are not. For the Toronto team, this was no comfort. They did not emerge from their experiment saying, it was only interference. They knew that the old dismissal had leaned on this explanation for years. What they proved was more subtle. Interference is not just a mathematical trick. It is recorded in matter. The atoms themselves bear witness to it. Negative time is not illusion, it is measurement. And this is where the unease returns. Because if negative time is real, even as interference, what does that say about the nature of time itself? What does it say about our faith in cause and effect? Imagine a film reel. Each frame plays in order, one after another, creating the illusion of motion. This is how we think of time. But now imagine that the reel itself can shift, that the frames can overlap and interfere, creating sequences where the story seems to jump ahead. The events are all there in the right order, but the interference makes them appear scrambled. That is quantum time. Not destroyed, not reversed, but reshaped into patterns that our minds cannot easily pass. Even Einstein, who bent space and time with relativity, preserved causality. Nothing could move faster than light. The order of cause and effect could not be broken. But quantum mechanics has always whispered of exceptions, not violations, but illusions that seem to defy the rules. Entanglement, where particles seem to share information instantly across vast distances. Weak values, where measurements yield results outside normal ranges. And now, negative time, where atoms record intervals that dip below zero. Each of these is a reminder that the universe is not bound by our intuitions. It is bound by mathematics. And the mathematics, strange as it may be, has never lied. Still, the human mind rebels. We crave stories. We crave arrows of time, causes leading to effects. And when confronted with interference that mocks those arrows, we tremble. But perhaps this trembling is the point. Perhaps negative time is not a violation of physics, but a violation of certainty. A reminder that the laws of nature are deeper than our metaphors, stranger than our comfort. The Toronto experiment shows us that interference is not just a curiosity. It is the fabric of reality. Time itself, as measured in the heartbeat of atoms, can be pushed and pulled by interference. And in those moments, what we call before and after cease to be absolutes. They become patterns. This does not mean we can build a machine to visit yesterday. It does not mean history can be undone. But it does mean that our experience of time, linear, forward, inevitable, is only a shadow of something richer, something wilder, something that, under the microscope of quantum physics, reveals cracks and folds where impossible things can occur. So no, it is not magic. It is not time travel. But perhaps it is something stranger. Because what if all of reality is interference? What if time itself, from the birth of the cosmos to the death of stars, is not a river, but a wave, one whose patterns may crest forward, backward, even sideways? The experiment in Toronto is small, a cloud of atoms, a pair of lasers, a team of patient physicists. But its implications echo outward. If negative time can emerge in this tiny chamber, then where else might it lurk? In the birth of galaxies, in the collisions of black holes, in the hidden symmetries of space-time itself. And if it lurks there, what does that mean for us? The fragile creatures who measure our lives in minutes and years, in causes and effects, in the forward arrow of time. Perhaps we are not passengers on a one-way river. Perhaps we are ripples on a wave riding patterns we barely perceive. And if so, then negative time is not an anomaly. It is a clue. A clue that the universe is stranger than we dare to imagine. We live our lives shackled to sequence. We wake, then we rise. We breathe in, then we breathe out. Our heart beats, and blood follows. To us, time is not just a measure, it is the framework upon which identity itself is built. We tell stories of beginnings and endings, of causes and consequences, of births and deaths. Without this order, meaning itself unravels, and yet negative time challenges that order. It whispers that before and after may not be absolutes, that the difference between cause and effect may not be fundamental but emergent, a pattern born from interference, like the crest of a wave that seems to leap ahead of its source. If this is true, then what is time to us? Is it the tyrant we imagine dragging us relentlessly toward the grave? Or is it a fragile story, stitched together by perception, dissolving when examined too closely? Philosophers have wrestled with these questions for millennia. Augustine confessed that he understood time until someone asked him to explain it. Kant argued that time was not a property of the universe, but a structure of the mind, a condition of experience rather than a thing in itself. And now, quantum physics intrudes, showing us measurements that seem to confirm their suspicion, that time is not an objective reality, but a construct woven from patterns. Consider what it means for an atom to return to rest before it is fully excited. To our language, this is contradiction, but to the mathematics, it is coherence. The interference of frequencies, the reshaping of waves, the reordering of events, all perfectly lawful. The contradiction arises not in nature, but in us. We cling to before and after because we need them. They are the scaffolding of narrative. Without them, the self dissolves. Imagine a life with no sequence, no arrow, only interference. Memories and predictions would lose distinction. You would not know if you were remembering the past or anticipating the future. You would not even know what past and future meant. In the Toronto experiment, the atoms do not care about these distinctions. They do not ask whether they were touched before they responded. They simply follow the laws of interference. Their testimony of negative time is not confusion, it is clarity. It is our insistence on sequence that falters. This raises a haunting question. Is time as we live it merely an illusion of scale? Do cause and effect only appear strict and absolute in the macroscopic world, while at the quantum level they dissolve into probabilities and patterns? If so, what does that make of us, who are built from those quantum parts? Imagine your life as a symphony. Each moment is a note, each decision a chord. But the symphony does not play in a straight line. Notes overlap, chords reverberate, harmonies interfere. At the grand scale, it sounds like melody. But at the microscopic scale, the order is not so clean. Some notes echo before they are struck. Some fade before they begin. Yet together they form a song that seems seamless. Is time the same? A melody that only appears linear from afar, but up close is nothing but interference. If so, then before and after are not the architecture of the universe. They are conveniences of perception, stories we tell ourselves so that existence can be endured. But if time is story, then who is the storyteller? The mind or the cosmos itself? Quantum mechanics has always unsettled us this way. It reveals a world where particles have no definite positions until measured, where cats are both alive and dead until observed, where entangled particles share states across light years. Negative time joins this chorus of discomfort. It shows us that even the sequence of events, the very bedrock of causality, may be less fundamental than we thought. And if causality is not fundamental, then what is? Some physicists argue that information, not time, is the bedrock, that the universe is not a story unfolding, but a tapestry of correlations. Time emerges from these correlations, like heat emerges from the random motion of molecules. It is not an entity, but a consequence. If that is true, then negative time is not a violation of nature, but a glimpse beneath its mask. A reminder that our categories, past, present, future, are conveniences, not absolutes. And yet to the human mind, the implications remain terrifying. Because if before and after are not absolute, then what becomes of responsibility? What becomes of memory? What becomes of the self? When you recall your childhood, you trust that it happened before this moment. When you plan for tomorrow, you trust it will follow today. If those distinctions are fragile, then what is identity itself but a trick of interference, a crest leaping forward from a wave of probabilities? This is why negative time is more than physics. It is philosophy with teeth. It forces us to ask whether existence itself is sequential or illusory. The Toronto experiment does not answer these questions. It only makes them impossible to ignore. The atoms have spoken, their testimony is clear. And we are left with the haunting echo, perhaps before and after are not what they seem. And if they are not, then who are we? Every great discovery is born into resistance. The more unsettling the revelation, the fiercer the denial. Negative time was no different. When the first whispers of early emerging light pulses were published decades ago, the scientific community split. A handful leaned forward, intrigued by the possibility that time itself might yield to quantum interference. But the majority leaned back, shaking their heads. To them, this was not revelation, but illusion, not breakthrough, but misinterpretation. They had good reasons for their caution. Physics is a discipline built on stability. Its laws do not bend to whim, and they do not tolerate fantasy. Time reversal was the stuff of science fiction, not science. The claim that atoms could record negative intervals was, to many, a bridge too far. Pulse reshaping, they repeated. The phrase became a shield, a mantra. The crest you see emerge early is not the crest that entered. It is a new crest, sculpted by interference. Nothing is moving backward. Nothing is escaping into the past. And in one sense, they were right. Negative time is not a time machine. It does not let us send messages to yesterday or undo mistakes. Causality, the chain of cause and effect, remains intact. But skeptics took this further. They argued that because causality was preserved, the entire phenomenon was meaningless. It was not negative time, they insisted. It was merely mathematics tricking our perception. To speak of negative time as real was to flirt with nonsense. For years, this dismissal carried weight. After all, who wanted to risk credibility by defending something that sounded like magic? Funding agencies were wary, journals cautious, reputations at stake. To most physicists, negative time was not a frontier to be explored, but a curiosity to be ignored. Yet the equations would not stay quiet. The mathematics of group velocity continued to yield predictions that dipped below zero. Again and again, the models insisted that under precise conditions, short pulses, resonant atoms, negative delays should appear. Still, skeptics countered with their mantra, illusion. If an experiment seemed to show negative time, it was simply the artifact of interference. No atom, no photon, no fundamental process had actually bent time. It is easy to understand this reluctance. Physics had been led astray before. Think of the luminiferous ether, once considered essential for light's propagation, later revealed as myth. Think of caloric theory, the mistaken belief in a fluid of heat. No one wanted to be the next fool chasing phantoms. But the Toronto experiment was different. For the first time, the atoms themselves recorded the anomaly. The probe beam revealed negative excitation intervals, matching the negative delays predicted by theory. The illusion, if it was illusion, had burned itself into matter. Still, skeptics resisted. Some argued that the measurement was not truly of time, but of phase. That the language of negative time was poetic at best, misleading at worst. Others suggested that weak measurements, the method underlying the probe, were themselves suspect, capable of producing values outside normal ranges that did not correspond to physical reality. Weak values, after all, have a reputation for strangeness. In some contexts, they predict particles with energies outside the possible spectrum, or spins pointing in impossible directions. Negative time, skeptics said, was just another artifact of this strange formalism. Nothing real, nothing physical, just mathematics stretched too far. But the defenders countered, if weak values are artifacts, why do they consistently match predictions? Why do they appear in carefully controlled experiments, verified across independent setups? Why, in this case, did the atom's response line up perfectly with the negative group delay of the pulse? The debate sharpened. On one side, those who saw in negative time a profound clue about the nature of temporal order. On the other, those who saw only the danger of misinterpretation, of granting reality to a metaphor. Steinberg himself acknowledged the controversy. "We don't want to say anything traveled backward in time," he said carefully. He knew the risks of language. To the public, negative time conjures visions of paradox and time machines. To physicists, it triggers reflexive skepticism. And yet, the data remained. The traces on the detectors were not illusions. The atoms had recorded intervals less than zero. Whether one chose to call it negative time or something else, the phenomenon was real. Perhaps the skeptics are right in a sense. Perhaps negative time is not time as we normally define it. Perhaps it is better understood as phase, as interference, as the shifting of probabilities. But even then, the unsettling truth remains. The universe allows intervals that mock our categories. And this is where skepticism becomes not a barrier, but a mirror. Because skepticism forces the question, what do we mean by time? What do we mean by measurement? What do we mean by reality? The skeptics fear misinterpretation, but their fear reveals the stakes. If negative time is real, then the arrow of time is not absolute. If it is illusion, then why does the illusion leave fingerprints in atoms? Either way, the mystery deepens. And perhaps that is the point. Physics thrives not on answers, but on questions that refuse to be silenced. Negative time is one such question. It forces us to confront the fragility of our categories, the limitations of our language, the strangeness of a universe that does not fit into our stories. For now, the skeptics remain unconvinced. But the Toronto experiment has tilted the balance. The old dismissal no longer holds. The taboo has been broken, and when taboos break, the frontier opens, which leaves us with a haunting possibility. If skepticism can no longer dismiss negative time, what new foundations must we build to understand it? And what if, in building them, we discover that time itself, this tyrant we thought unyielding, is only a shadow of something deeper? Science lives or dies in the space between prediction and observation. Theories may be bold, elegant, even beautiful, but if their numbers do not survive contact with experiment, they are abandoned. Nature is indifferent to cleverness. It obeys only itself. For years, negative group delay lived in the uneasy realm of prediction. Equations suggested it should be possible, pulses emerging early, atoms recording intervals less than zero. But predictions without proof are fragile things. They can be waved away, dismissed as artifacts of the mathematics. Skeptics leaned on this fragility for decades, until the day the data arrived. When Steinberg and Angulo fired their faint light pulses into the cloud of rubidium atoms, they were not looking for miracles. They were looking for patterns. They varied pulse durations. They adjusted atomic densities. They tuned the probe beam. Each run was another point in a vast map, each number another brushstroke in a picture yet unfinished. And as the data accumulated, a shape emerged. Negative times appeared exactly where theory had said they would. Short pulses, resonant interactions, particular configurations of density. The predictions were not vague, they were precise. And the atoms answered with equal precision. This was no coincidence. This was no anomaly. The experimental curves matched the theoretical ones with uncanny accuracy. The negative excitation times of the atoms mirrored the negative group delays of the pulses. Like two instruments in harmony, the mathematics and the measurements played the same tune. For skeptics, this was the hardest truth to face. Illusions are not so obedient. Tricks of perspective do not follow predictions with mathematical fidelity. If negative time were mere artifact, it should appear inconsistently, unpredictably. But it did not. It appeared when and where it was expected, and nowhere else. This is the power of physics at its best, not just observing the strange, but predicting it. To see negative times emerge where equations foretold them was to confirm that the strangeness was not accidental. It was woven into the fabric of the laws themselves. It is difficult to overstate how unsettling such confirmation is. Predictions that defy intuition are easier to dismiss. But when reality itself conspires to prove them true, the dismissal falters. The Toronto experiment forced a reckoning. If the atoms recorded negative times in perfect agreement with theory, then negative time was not an illusion. It was real as any other measured quantity in physics, and yet reality here wears a mask, because while the numbers align, our minds do not. We crave sequence. We crave cause and effect. To accept negative time as real is to admit that our categories are insufficient, that the universe plays by rules we cannot narrate in human language. Still, the numbers were undeniable. When theory predicted a shift forward, the atoms responded in kind. When it predicted none, the atoms were silent. The harmony was flawless. Consider what this means. In physics, the gulf between theory and experiment is usually wide, bridged only through effort. Predictions are approximate, observations noisy. Agreement is measured in tolerances, margins of error. But here, the agreement was exact. The atom's heartbeat and the equation's rhythm were indistinguishable. It was as if reality itself had leaned over to whisper, "Yes, this is true." For Steinberg and his colleagues, this was vindication. Years of doubt, of skepticism, of dismissal fell away in the face of numbers that refused to be ignored. They had not stumbled into an illusion. They had confirmed a truth. But confirmation is not the end. It is the beginning of a new set of questions. If theory and experiment agree, then the phenomenon is real. But what does it mean? What does it tell us about the nature of time, of causality, of the universe itself? Some physicists argue that negative time is not time in the sense we live it. It is a property of wave interference, a reshaping of patterns. Others counter that this distinction is meaningless. If matter records negative intervals, then those intervals are as real as any other. What both sides cannot deny is the match. Prediction and measurement are inseparable now. Negative time is no longer a ghost in the equations, it is a fact in the data. This alignment also hints at something deeper, the extraordinary power of mathematics to reveal truths that defy intuition. Long before the Toronto experiment, the equations whispered of negative time. The human mind recoiled, but the mathematics was indifferent. It carried within it a map of a world stranger than imagination. This is the paradox of science. Our intuitions fail, but our equations succeed. We do not understand, but we can predict. And in those predictions, we find truths that change us. Negative time is one such truth. It tells us that the universe is not constrained by our sense of order, that before and after are not absolutes, but outcomes of interference, that even atoms, in their quiet stillness, can defy our categories. For the skeptics, this remains hard to swallow. To concede that negative time is real is to concede that time itself may not be fundamental. But the numbers do not bend to preference. They align too perfectly. And so, theory and experiment together force us forward. We can no longer hide behind dismissal. We must ask the harder questions. If time can be negative in the heart of an atom, what does that mean for the arrow of time in the cosmos? If the laws of interference can bend intervals here, can they bend them in the collisions of black holes, in the birth of galaxies, in the fabric of space-time itself? The Toronto experiment does not answer these questions, but it ensures they can no longer be ignored. Because when theory and reality sing the same song, you are compelled to listen. And what they sing now is a haunting refrain. Time is not what you think. Measuring the quantum world is like trying to read words on the surface of water while stones are falling into the pond. Every attempt to observe creates ripples, distorting the very thing you seek to see. This is the paradox at the heart of quantum mechanics. Observation is participation. To measure is to interfere. For most of physics, this is not a problem. Macroscopic objects, planets, pendulums, machines, can be measured with negligible disturbance. But at the scale of photons and atoms, the disturbance is everything. A strong measurement collapses possibilities into a single outcome. The quantum wave function, once broad with potential, collapses into one state under the harsh spotlight of observation. But what if you could measure without collapsing? What if you could ask the universe a question so gently that it barely notices, leaving the fragile superposition intact? This is the idea of weak measurement. Weak measurement does not grab the system and force it to answer. It whispers. It brushes past with the faintest touch, nudging probabilities rather than dictating outcomes. The answers it yields are strange, sometimes nonsensical, results outside the normal range of possibility, values that defy expectation. But these weak values, as they are called, contain information that strong measurements destroy. It was this method that Steinberg's team used to listen to the heartbeat of their rubidium atoms. The probe beam was tuned not to hammer the atoms into a response, but to tickle them, to sense their state without collapsing it. By correlating the probe's tiny shifts with the single photons detected from the signal beam, the team could reconstruct the atom's excitation times, and this was where the impossible appeared. Because weak measurements, unlike strong ones, can yield values that lie outside the expected range. Negative times are one such value. To skeptics, this is proof that weak values are illusions, mathematical oddities with no physical meaning. They point to weak measurements that have produced particles with negative energy or spins greater than 1, results that seem absurd. Why trust such numbers? But defenders counter that weak values, strange as they are, have predictive power. They appear where theory predicts they should. They repeat across experiments. And in the Toronto case, they matched the negative group delays perfectly. If they are illusions, then they are illusions with unnerving consistency. Consider the philosophical weight of this. A strong measurement tells you one truth, blunt and final. A weak measurement tells you a ghost of a truth, a value that may be outside the range of normal, but that captures something the strong measurement cannot. It is like hearing an echo of a song that has not yet been sung, a glimpse of a shadow from an object not yet present. Weak measurement blurs the line between reality and interpretation. It raises the question, what does it mean for something to be real in the quantum world? If negative time appears in a weak value, does that mean time itself can be negative, or that our measurement has revealed only a shadow, a ghost in the mathematics? Steinberg himself acknowledges this ambiguity. He does not claim that photons traveled backward in time. He does not claim atoms truly anticipated the future. Instead, he frames negative time as one way of describing results that fit both theory and experiment, a description, not a declaration. And yet, the numbers remain. The atoms, under weak measurement, record intervals less than 0. The predictions match. The data holds. Whether we call this reality or ghost, it is still there, etched into the experiment. This is the unsettling power of weak measurement. It opens a door into regions of physics where our categories falter. It reveals values that cannot exist under strong observation, but that nonetheless shape the system. It is as though the universe, when asked gently, whispers secrets it will deny if pressed. What does one do with such secrets? Do we dismiss them as illusions, comforting ourselves with the certainty of strong measurements? Or do we lean into them, accepting that reality may be richer and stranger than our categories can contain? The answer may depend on how we define reality itself. Is reality only what strong measurements confirm, definite outcomes, bounded values, measurable durations? Or is reality also the ghostly hints the weak values that reveal the shape of things that cannot otherwise be seen. If the latter, then negative time is not illusion, it is revelation. It tells us that time is not a simple arrow, but a spectrum of possibilities, some of which point backward. Imagine standing at the edge of a forest. In daylight you see trees clearly, solid and distinct. This is the world of strong measurement. But at twilight, the forest becomes a play of shadows. Shapes overlap, hints of movement flicker at the edges of vision. This is the world of weak measurement. And sometimes in the twilight, you glimpse truths the daylight conceals. Negative time is such a truth. It does not overturn causality. It does not grant us paradox machines or journeys into the past. But it shows us that the fabric of time is not as rigid as we thought, that before and after are not absolutes, but patterns that can be bent under the pressure of interference. And if weak measurement can reveal this, what else might it show us? What other ghosts lie in the twilight of the quantum world, waiting for us to ask the right question, softly enough to hear their reply? The skeptics remain unconvinced. To them, weak values are curiosities, not realities. But the Toronto experiment forces the question. Because if weak values are meaningless, why do they match theory so perfectly? Why do they appear exactly where predicted, and why do atoms bear their imprint? Perhaps weak values are not illusions. Perhaps they are glimpses of a deeper layer of reality, one where time itself is not linear, but fluid, one where cause and effect are not absolutes, but probabilities, one where the universe does not march, but dances. And if this is true, then weak measurement is not a trick, it is a key to doors we did not know existed. Doors that lead into the heart of reality, where time can be negative, where shadows can precede the objects that cast them, and where the impossible becomes measurable. The phrase negative time strikes like thunder. It conjures visions of paradox, of messages sent to the past, of footprints forming before the step. For the public, it suggests the machinery of time travel. For scientists, it threatens something even more sacred, causality. Causality is the spine of physics. It is the principle that causes precede effects, that every action has a consequence, and that those consequences never reach backward. Without causality, science collapses. If causes can follow effects, then prediction is meaningless. Experiments yield no knowledge, only chaos. So when Steinberg's team revealed their measurements, the first question from skeptics and believers alike was the same. Does this break causality? The answer is no. Negative time does not undo the chain of cause and effect. It does not allow messages to be sent into the past. It does not permit paradox. The speed of light remains unbroken, the arrow of causality unbent. How, then, can atoms record negative intervals? How can photons appear to emerge before they arrive if the sacred order remains intact? The key lies in interference. Each photon pulse is a blend of frequencies. These frequencies shift as they pass through atoms, some delayed, some advanced. When recombined, the pulse's crest can leap forward. The atoms tuned to this reshaped crest record their excitation accordingly. Nothing has traveled backward. No effect has preceded its cause. The pulse has simply reshaped itself, and the atoms have borne witness to that reshaping. Negative time emerges not as a violation of causality, but as an artifact of interference. Yet this reassurance is double-edged, because while causality survives, our understanding of time does not. The order of events remains intact, but the intervals between them bend in ways that defy intuition. Time is preserved but distorted. Think of a river. Its water always flows downhill, always forward. That is causality. But within the river, eddies swirl, currents fold, waves leap ahead. These distortions do not reverse the flow, but they mock its simplicity. To the fish caught in an eddy, the river's forward current becomes irrelevant. The local motion contradicts the global rule. Negative time is such an eddy. Locally, atoms record intervals that are less than zero. Globally, causality persists. Both are true, and both must be accepted. This is the strange compromise of quantum physics. It preserves the sacred laws while undermining the certainty with which we understand them. It gives us safety with one hand and mystery with the other. Steinberg himself was careful to stress this point. "We don't want to say anything traveled backward in time," he explained. It was a necessary caution to prevent misinterpretation. But in saying so, he also admitted the strangeness of the result. Because even if causality survives, our categories, before, after, duration, delay, are no longer absolute. This survival of causality is not just philosophical reassurance. It is essential for technology. Quantum computers, quantum networks, quantum sensors all depend on the reliability of cause and effect. Engineers cannot build systems on paradox. They need rules, and the rules, however strange, remain. But the survival of causality should not lull us into complacency, because what negative time shows is that causality's survival is more fragile than we thought. It survives not as an inviolable truth, but as a delicate balance in the interference of waves. One step deeper, one layer further, and the categories we trust dissolve into ambiguity. In this sense, negative time is not a violation but a warning. It tells us that the order we cling to is conditional. It holds, but only because the universe permits it, not because it is inevitable. Imagine standing on a frozen lake. The ice beneath you feels solid, absolute, but crack the surface and you see the water beneath, flowing, shifting, alive. Causality is like that ice. Negative time is the crack. It does not plunge us into chaos, but it reminds us that beneath our certainties lies turbulence. This is why the discovery is both comforting and unsettling. Comforting because no paradox emerges. Unsettling because the comfort is conditional, fragile, contingent. And so the question lingers. If causality can survive even when atoms record negative time, what else might it survive? Could space-time itself harbor distortions that mock our intuitions, yet preserve the chain of cause and effect? Could black holes, wormholes, or cosmic entanglement conceal intervals that appear negative, yet leave the arrow unbroken? If so, then causality is not the rigid backbone of the universe we once imagined. It is a thread stretched taut across storms of interference, holding firm only because it must. This realization is both humbling and awe-inspiring. It shows us that the laws of physics are deeper than our categories. They do not yield to paradox, but neither do they yield to intuition. They survive, but they do so by reshaping themselves in ways we cannot easily comprehend. The Toronto experiment proves this point with merciless clarity. The atoms recorded negative times. The theory predicted them. The match was perfect, and yet causality endured. The universe did not unravel. But if the universe can permit such strangeness while preserving order, then what else might it permit? What other illusions of impossibility might lie hidden, waiting to be revealed? Negative time does not give us time travel, but it gives us something stranger, a universe where the impossible can occur without breaking the possible, a universe where paradox and order are not enemies, but partners. And in this partnership lies the deepest mystery of all, because if causality can survive even here in the shadow of negative time, then perhaps it is not merely a law, but a principle woven into the fabric of existence itself. Or perhaps, and this is the darker thought, causality survives only by chance, a fragile accident of interference, one that might not hold under conditions yet untested, which raises a question too large to ignore. What happens if one day we find the place where causality does not survive? Time is the most intimate of illusions. We do not merely observe it, we live inside it. Every memory, every plan, every heartbeat is chained to its arrow. We imagine it as a straight line, unbroken and absolute, carrying us from birth to death, from past to future. Human time is narrative, and we are its characters. But quantum time is something else entirely. At the scale of photons and atoms, the arrow bends, splits, and sometimes dissolves. The neat distinction between past and future collapses into probabilities. Events blur into one another, overlapping like ripples on a pond. What we call before and after become less fundamental than the interference patterns that produce them. The Toronto experiment makes this plain. To us, the idea of negative time is paradox. To atoms, it is simply measurement. Their excitation and relaxation do not obey our storybook version of time. They obey mathematics, they obey interference, they obey rules that make sense only in the quantum domain. The gulf between quantum time and human time is vast. On one side, we tell ourselves stories. On the other, reality operates as equations. Somewhere in between, the two must reconcile. But the reconciliation is uneasy, fragile, and incomplete. Consider memory. For us, memory defines the past. We know an event has occurred because we recall it. But in physics, memory is irrelevant. Atoms do not remember in any human sense. They simply respond to the fields around them, registering interactions without narrative. Their testimony of negative time is not a memory, it is a correlation. Consider also anticipation. For us, the future is unknown, shaped by choices yet to be made. But in quantum mechanics, the future can influence the present. Through the mathematics of post-selection and interference, outcomes not yet realized can leave traces in present measurements. Negative time is one such trace. The atom's responses reflect not only the incoming photon, but the interference of all possible frequencies, some of which crest ahead of expectation. In this way, quantum time mocks human categories. Past and future blur. Cause and effect twist into spirals. Where we see paradox, the equations see harmony. And yet, we cannot live inside quantum time. Our lives unfold in the macroscopic world, where probabilities collapse into certainties, where eggs do not unbreak, where footsteps do not precede the walker. Decoherence ensures this. The fragile superpositions of the quantum world collapse when scaled upward. The wave dissolves into the arrow. Human time emerges as the average story of countless quantum interactions. But what if this emergence is only partial? What if human time is not a separate reality, but a shadow of quantum time, a simplification, a smoothing over of the turbulence beneath? If so, then negative time is not an aberration. It is a glimpse into the raw foundation from which our arrow emerges. Philosophers have long suspected this. Augustine wrote that time was a mystery even to those who lived it. Kant argued that time was a condition of human perception, not of the world itself. Modern physics, in its cold precision, now gives their suspicions experimental teeth. The unsettling truth is that human time may not be real in the way we think it is. It may be a construct, a story generated by consciousness to navigate a universe of interference. We feel the river flowing forward, but beneath us, the water churns in eddies, some swirling backward, some forward, all merging into a current too complex to perceive. This is why negative time feels so disturbing. It is not that it breaks causality. It does not. It is that it reveals the fragility of our narrative. It reminds us that our sense of time is not the universe's truth, but our adaptation, a map, not the territory. And yet this adaptation is everything to us. Without it, identity collapses. Without before and after, memory and anticipation dissolve. Who are we if not creatures of time, defined by sequence, chained to an arrow we cannot escape? The Toronto experiment forces us to ask, are we wrong to think of ourselves this way? Or are we right, but only at a certain scale? Perhaps human time is not false, but emergent, like temperature, which arises from countless particles in motion, but has no meaning at the level of one. If so, then negative time is not an insult to human experience. It is a reminder that our experience is partial, that beneath our narrative lies a deeper truth, But that reminder is not comforting. It is humbling. It shows us that the universe does not conform to our stories. It allows us to live them, but it does not share them. What does this mean for the future of physics, for philosophy, for us? If human time is a construct, then perhaps we can reshape it. If quantum time allows intervals less than zero, then perhaps the arrow we cling to is not destiny, but design. Could we one day learn to manipulate time at the quantum level, just as we manipulate electrons in circuits? Could we one day bend the arrow, not in paradoxical reversal, but in practical control? Quantum technologies already hint at this. Quantum computers exploit superpositions that defy linear sequence. Quantum networks exploit entanglement that disregards distance. Perhaps negative time, too, will find use. Not in science fiction paradoxes, but in the engineering of systems that harness interference in ways we cannot yet imagine. For now, it remains mystery, a crack in the ice of our certainties, showing the turbulence beneath. But even as causality survives, even as our lives continue to unfold in orderly sequence, the crack remains. And it whispers, "Your time is not the universe's time." What does it mean to live as creatures bound to narrative when the foundation of reality is not narrative at all? What does it mean to cling to before and after when atoms themselves do not? It is tempting to treat negative time as little more than philosophical theater, a curiosity for physicists, a thought experiment for philosophers, a headline for journalists. Strange, yes, but of no consequence to the practical world. But this would be a mistake. Because in science, the strangest discoveries often prove to be the most useful. Electricity once seemed like a parlor trick, magnetism a curiosity. Quantum mechanics itself began as an attempt to explain spectral lines and photoelectric quirks. Today, they are the engines of civilization. Negative time may one day join their ranks. At its heart, the Toronto experiment was not about time travel or paradox, it was about control. Control over the interaction between photons and atoms, the very heart of quantum technology. In this dance of light and matter lies the future of computation, communication, and sensing, the pillars of the coming quantum age. Quantum computers promise to solve problems beyond the reach of classical machines, simulating molecules, optimizing complex systems, breaking cryptographic codes. But to build them, engineers must choreograph photons and atoms with exquisite precision. Each interaction, each exchange of energy, must be measured and manipulated down to fractions of a nanosecond. This is where negative time matters. The discovery that atoms can register intervals less than zero shows that these interactions are richer than we thought. By understanding how interference reshapes excitation, scientists can better predict and control the behavior of photons in quantum systems. What once seemed an anomaly becomes a tool. Consider quantum networks, the dream of transmitting information not through wires, but through entangled photons spanning continents. The reliability of these networks depends on precise control of light pulses as they move through matter. If those pulses can shift forward, if their peaks can be reshaped by interference, then engineers must learn not only to accommodate the effect, but to harness it. Negative time, once dismissed as illusion, becomes a parameter to be engineered. Even quantum sensing, the use of fragile superpositions to measure gravity, magnetism, or acceleration with unprecedented accuracy, may benefit. Tiny shifts in timing, once thought meaningless, now reveal new ways to push sensitivity further, to measure the imperceptible with clarity. But the implications reach deeper still. Because negative time is not just a quirk of rubidium atoms and faint light pulses. It is a window into the hidden rules of quantum mechanics. Rules that, if mastered, could unlock technologies we cannot yet imagine. Think of how relativity gave us GPS. No one built satellites in 1915. Yet Einstein's equations, strange and abstract, became essential for a technology woven into our daily lives. Think of how quantum tunneling, once a bizarre prediction, now underpins every microchip on Earth. Negative time may be next. Its strangeness may hide practical power. Of course, the path is not clear. Even Steinberg admits he sees no immediate application. The discovery is too new, too raw. But history is filled with such beginnings. Lasers were once a solution in search of a problem. Today, they scan our groceries, guide our surgeries, carry our internet. The lesson is simple. Strangeness is no barrier to utility. Sometimes it is the very source of it. Yet the implications are not merely technical, they are also conceptual. By proving that atoms can record negative intervals, the Toronto team has expanded the toolbox of physics. They have shown that even impossible-sounding phenomena can be measured, confirmed, and studied. This emboldens researchers to probe deeper, to ask questions once considered untouchable. If negative time is measurable, what else might be? What other illusions might yield to experiment, revealing themselves as hidden truths? Already whispers circulate of connections between negative time and broader questions, the arrow of entropy, the mysteries of entanglement, the fabric of space-time itself. Could the interference that produces negative time also illuminate how time emerges from quantum correlations? Could it inform theories of quantum gravity, where space and time themselves are thought to be emergent phenomena? If so, then the implications stretch far beyond engineering. They reach to the deepest foundations of physics. Still, we must return to the practical. For the engineers building the quantum age, negative time is not a philosophical indulgence. It is a parameter to be mastered, a puzzle piece in a vast design. Understanding how and why atoms register these strange intervals may help them build systems that are faster, more precise, more reliable. And for the rest of us, it is a reminder that the technologies of tomorrow often emerge from the impossibilities of today, that the strangeness of the lab may become the infrastructure of civilization. So, is negative time useful? Today, perhaps not. Tomorrow, almost certainly. Because physics is not just about what is true, it is about what is possible. And when possibility expands, so too does our power. Yet with this power comes unease. To harness negative time is to admit that time itself is not absolute, that the categories upon which we build our lives can be bent, reshaped, engineered. What does it mean if one day we can design the flow of time at the quantum level, just as we design circuits and code? What would it mean to live in a world where before and after could be tuned, adjusted, manipulated? This is no longer just a question for engineers, it is a question for humanity. Because if negative time becomes not just a measurement, but a tool, then the future will not simply be built on the arrow of time, it will be built on its bends. And that future will not only be stranger than we imagine, it will be stranger than we can imagine. The laboratory is small, a chamber, some lasers, a cloud of atoms, and yet, in that modest room in Toronto, the arrow of time cracked. A measurement, delicate and precise, revealed intervals that bent backward. Negative time. It would be tempting to leave the mystery there, confined to the quantum domain, a curiosity of photons and atoms, strange but irrelevant to the wider universe. But to do so would be to forget how often the smallest scales mirror the largest. The same mathematics that governs electrons shapes galaxies, the same laws that bind atoms sculpt black holes. If negative time is real in the lab, then what might it mean for the cosmos? To answer, we must venture into realms where our understanding of time is already fragile. The collapse of stars, the birth of the universe, the fabric of space-time itself. Begin with black holes. These cosmic abysses bend time more violently than any other object. To an outside observer, matter falling into a black hole slows, stretching toward infinity, never quite crossing the event horizon. To the matter itself, time rushes on, crossing the boundary in an instant. Two realities coexist. One where time freezes, one where it flows. What happens then to light at the threshold? What interference patterns emerge when space-time itself is reshaped? Could the strange intervals recorded in Toronto also whisper in the shadows of black holes, places where cause and effect already blur, where before and after lose their meaning? Some physicists suspect so. Negative time, they argue, is a local distortion of interference. Black holes may produce distortions of unimaginable scale. If atoms can record negative intervals, what might an event horizon record? Could it harbor negative temporal signatures, intervals where the universe itself seems to anticipate its own collapse? And what of the beginning, the Big Bang? At that singularity, time itself is said to have begun. But what does it mean for time to begin? If negative intervals are real, could the birth of the universe have included stretches of negative time? Echoes before the explosion, shadows cast backward into nothingness? These questions are speculative, dangerous even, but they are no more speculative than relativity once was, or quantum mechanics itself. And speculation is not fantasy when it springs from measurement. The atoms in Toronto testified to negative time. That testimony, however local, forces us to imagine its cosmic echoes. Imagine a universe where time is not a river but an ocean, currents flowing in all directions, some forward, some backward, some sideways. Most of the time we ride the dominant current, the forward arrow. But occasionally, in hidden eddies, time folds against itself, forming negative intervals. The Toronto experiment shows us one such eddy. Black holes may conceal others. The birth of the cosmos may have been saturated with them. And if this is true, then what of the future? If negative time is woven into the fabric of the universe, then perhaps it will emerge not only in the laboratory, but in the fate of galaxies, in the collisions of stars, in the ripples of space-time itself. Already, gravitational wave observatories detect distortions in space-time as black holes collide. Could future detectors, more sensitive, uncover temporal signatures, negative intervals hidden in the fabric of those waves? Could we one day measure the universe anticipating itself, time folding before the impact? To think this way is to step beyond science as we know it. But it is also to honor the spirit of science itself, to follow the evidence, however unsettling. Because what negative time shows us is that the impossible is not always impossible. Sometimes it is simply hidden, waiting for the right experiment to reveal it. The implications are staggering. If negative time is local interference, then the cosmos itself may be interference on a grand scale. Galaxies, black holes, even the universe itself may harbor temporal distortions beyond imagination, and if they do, then our story of time, linear, absolute, unyielding, collapses. We are left with something stranger, a universe where time is pattern, not arrow, where before and after are not absolutes but approximations, where the unthinkable is not forbidden, only rare. This is the frontier we now face. Not the frontier of faster-than-light travel or paradoxical machines, but the frontier of understanding, a frontier where time itself is no longer safe. The Toronto experiment cracked the door. The cosmos may fling it wide, and so we must ask, if negative time exists in the smallest chambers of the quantum, and perhaps in the largest cathedrals of the cosmos, then what is time at all? Is it our most trusted measure, or our most persistent illusion? We began with a question that should never have been asked. Can time itself be negative? And we end with an answer that is no answer at all. Yes, atoms can record intervals less than zero. Yes, photons can emerge ahead of themselves. But what this means, for physics, for philosophy, for us, remains unsettled. The story of time is older than science. It is written in myths and religions, in the rise and fall of civilizations, in the rhythms of the stars. The ancients saw time as cyclical, repeating in endless returns. The moderns imagined it as a line marching forward, and now quantum mechanics forces us to imagine it as neither, but as something stranger, a pattern, woven from interference, sometimes pointing forward, sometimes back, always elusive. The Toronto experiment is not the first to challenge time's authority, nor will it be the last. Einstein bent time with relativity, showing that its flow depends on speed and gravity. Quantum mechanics shattered its continuity, reducing it to probabilities. Negative time now adds a new fracture, the possibility that even sequence itself is conditional. And yet, through all these revelations, we persist. We live as creatures of narrative. We cannot help but tell stories of before and after, of cause and effect, of lives that begin and end. Negative time does not change this. It cannot. For us, the arrow holds, because without it, there is no us. But what negative time does is remind us that our experience is not the universe's truth. It is a shadow, a simplification, a melody drawn from a symphony too vast to comprehend. The atoms in Toronto whispered this to us, that the story we tell ourselves is incomplete, that beneath our arrow lies turbulence, eddies, distortions, moments where time bends against itself, where the impossible becomes measurable. This is not paradox, it is revelation. The revelation that time, like all things, is more complex than it seems. So what do we do with this revelation? Do we dismiss it as skeptics once did, soothing ourselves with the comfort of narrative? Or do we embrace it, unsettling as it is, and let it reshape our understanding of existence? Perhaps the choice is not ours. The universe does not ask our permission to be strange. It simply is. And yet, there is hope in this strangeness. For if time can bend, then so too can possibility. The technologies of tomorrow will be built not on the certainties of today, but on the mysteries that unsettle us. Negative time may become a tool, a key, a stepping stone to a future we cannot yet imagine. But even if it does not, even if it remains only a curiosity, it has already transformed us, because it forces us to look at time not as a tyrant, but as a question. And in that question lies freedom. Imagine, for a moment, that the arrow of time is not absolute, that your past and your future are not separate realms, but overlapping patterns. That memory and anticipation are two sides of the same interference. Would you live differently? Would you see your life not as a march toward an ending, but as a ripple in a pattern larger than yourself? This is the story negative time tells us, that we are not bound as tightly as we think, that the categories we cling to, before, after, cause, effect, are fragile, provisional, that the universe allows more than our stories can contain. And so we end where we began, with a question. What is time? Is it the arrow we live, the interference we measure, or something deeper still? The Toronto experiment does not answer. It cannot. But it opens the door, and through that door we glimpse a truth that is both terrifying and beautiful. Time is not what we think it is. Perhaps it never was. Perhaps it is not a river, not a line, not even a cycle. Perhaps it is a song, complex, dissonant, filled with harmonies we cannot hear, rhythms we cannot follow, crescendos that leap ahead of their own notes. And we, fragile listeners, cling to the melody, calling it past and future, before and after. But the song itself is wilder than we know. In the end, negative time does not give us control. It gives us humility. It reminds us that the universe is larger than our categories, stranger than our certainty, deeper than our comprehension. And in that reminder perhaps lies the truest story of time, not as an arrow, not as a cycle, but as a mystery that defines us, eludes us, and will always lie just beyond our reach. The experiment is over. The atoms have spoken. The detectors have gone silent. But the question remains, echoing into the cosmos. What is time? And if even atoms cannot tell us, who can? Thank you for joining us on this extraordinary journey through the universe here on Frontiers of Infinity. If this glimpse into the unknown has sparked your curiosity, be sure to subscribe and join us, where we unravel the darkest mysteries of space.